Okay, we've looked at centroids of areas, and we just looked at centroids of volumes. The next thing we're going to look at is centroids of lines. Okay, so here we have a line, and it's not just a straight line. It could be any shaped curve, and it's a curve that is in 3 dimensions. If I consider a little segment of the line, dl, then I can say that that dl is going to have some coordinates. It's going to have an x-coordinate, a y-coordinate, a coordinate along the z-axis. That is going to locate that segment dl and give us the position of that little piece of the line. And if I break the line into multiple segments along the curve and I find the position of each of those segments, I could then average all the x values, all the y values, all the z values, and get the centroid of the line. That is the average position of all the little pieces that make up that line. And of course, the formula is just the same formula that we've seen for areas and volumes, but instead of being over dA or over dV, it's over dl, the length of that tiny little piece. And so the formula for the x centroid is the integral of x dl divided by the integral of dl, with similar forms for the y centroid and the z centroid. And as you might have guessed based on what we've done before, the trick to doing these integrals is going to be figuring out what these dl values are. The easiest way to do this is to perhaps consider an example. So this is an example from your textbook, and it is to find the centroid of the parabola y equals x squared along the path from the origin, 0, 0, to the point 1, 1. So this is an arc of a parabola of a finite length, and we want to find the centroid, that is the average position of all the little pieces that make up this line. So let's consider a little piece of the line of length dl, and I'm going to blow this up. So I've got this segment here that is of length dl, and it could break that piece up into a dx and a dy, and then by the Pythagorean theorem I could say that dl squared is equal to dx squared plus dy squared, and I could then solve that for dl squared, or rather solve it for dl, and that would just be the square root of dx squared plus dy squared, and that's going to be the length of dl just by applying the Pythagorean theorem. Now if we look at what we have here, we've got our dl is equal to dx squared plus dy squared under the radical. We can rearrange this a little bit. Look at this form right here. That is going to be something that we want to consider. How do you go from here to there? One clue is that there's this dx out here, but there's not a dx by itself on the left-hand side of this equation. So what they've done here, you can see they've got a dx squared here, they've got a 1 there. They've basically factored out the dx. So we could write that as dx squared square root times 1 plus dy over dx squared, and that is how we can factor out that dx. And of course the square root of the square just gives us dx times the stuff under the radical, and that is what we see here. So this is the formula for the value of dl. Now this dy over dx, that's just the derivative. And so here we have the derivative squared. Now what's the derivative of our function here? We know that y is equal to x squared, and so the derivative y prime, or dy dx, is just going to be 2x. Now of course we want to have that squared, so y prime squared is equal to 4x squared. And that's the value that we would plug into here for this specific problem of doing the parabola. So now we have our dl for the parabola, and specifically it's the parabola y equals x squared. And again, we're on the interval from the origin to the point 1, 1. What do we do with that? Well, we're going to plug this into our centroid formula. So we can say we know that it's x dl integral over the integral of dl. And when I plug this guy in, I'll transform this to an integration not over dl but over dx. And then if I want my limits of integration, what does x range from? Obviously it ranges from x equal to 0 to x equal to 1. And so that'll be the limits of my integration. So if I plug those values into the formula, I get this integral here from 0 to 1 of x times the square root of 1 plus 4x squared dx divided by the integral from 0 to 1 of 1 plus 4x squared dx. And so you just do those two integrals, very simple, and you spit out the answer. At least that's what your textbook does. It just basically goes from there to the answer. It might have left out a couple of steps, and I just wanted to kind of show you guys how to do these integrals. I know you've seen it before, but sometimes a review can be helpful. We have two integrals to do, the numerator and the denominator, so we're going to start with the numerator, which is x times this expression 1 plus 4x squared under the radical, integrated over dx. And of course, you might recognize that the best approach for this is a simple trig substitution. If we let u equal to 1 plus 4x squared, that's what's under the radical, then the du is simply going to be gotten by taking the derivative of that. The derivative of 1 is 0. The derivative of 4x squared is 2, comes down, it makes it 8x, and then I bring the dx over so that getting du by itself is equal to 8x dx. And if I plug those values in, the integral becomes 1/8, 1 to the 5, square root of u du. Now, I want to mention just for a moment, how did I get those limits? Because we had a limit change. The limit went from 0 to 1, and then from 1 to 5. And the way that I get that is I simply plug in the values for my u. So, for example, if x equals to 0, that means that u is equal to 1 plus 4 times 1 plus 0 squared. And so that means that u is equal to 1, because this 4x squared term goes away if x is equal to 0. And then for the limit x equal to 1, I simply plug in a 1 there. 1 squared gives me 1 times 4 is 4, plus 1, and that gives us 5. So if x is equal to 1, that means that u is equal to 5. And so we have a limit change that we've done, and we can simply plug those limits in right there, and that will let us do this integral. The integration itself is now very straightforward. U to the 1/2 du is, the integral of that is 2/3 u to the 3/2, and multiply that by 3/8, or I'm sorry, multiply that by 1/8, and you get 1/12, 5 to the 3/2 minus 1 to the 3/2, and that works out to be 0.8483, and that is the answer, that's the value of this definite integral, which is the numerator in our example. Now we can look at the denominator. The denominator is does not have the x here. It's just 1 plus 4x squared. And so u substitution is not going to be very useful here, but you might think, looking at this form, that a trig substitution might help, and you would be right. That's where you want to start. The appropriate substitution is going to be x equal to 1/2 the tangent of u. If I plug in 1/2 squared, I get 1/4, so that gets rid of that 4, and then I have 1 plus tangent squared, and that, of course, is a trig identity that I can simplify. So that's going to be my substitution. X is equal to 1/2 tangent of u. Then dx is going to be 1/2 the secant squared of u du. That's just taking the derivative of the tangent. And of course, I can solve this for u, and u is going to be the arctangent of 2 times x. So I can now use this substitution. I can put this substitution into my integral. So what I have here is this term here is my square root of 1 plus 4x squared. I've substituted in for x. And then this term is just simply my dx. And so this is my f of x here. This is my dx. And I know that this value, 1 plus tangent squared, there's a trig identity that's equal to secant squared. And the square root of secant squared is just secant, so I have secant times 1/2 secant squared du, and that's just 1/2, which can obviously come out front, times the cube of the secant du. So 1/2 secant cubed of u du. That is our transformation with this substitution. Sadly, this transformation, it's a step in the right direction, but this is still a pretty tricky integral to do. How do you do the integral of secant cubed? Well, one of the things that you can do is you can break it up into secant times secant squared. And so if I think of an integral like that, secant of x times secant squared of x, that's an integral that can be done by breaking it up into parts. And so I'm going to break this integral into parts and do an integration by parts to further get to the end. So if you look at the formula for the integration done by parts, if you have an integrand of the form u dv, you can break it up into u times v minus the integral of v du. Now our integral is secant of x, secant squared of x dx, and so I'm going to let this part be my u, and then that part be my dv. So if u is the secant of x, then du is simply obtained by taking the derivative, and that gives me secant of x times the tangent of x dx. And if dv is equal to this part here, secant squared of x dx, well, the integral of that is just tangent of x. And that leaves us with secant cubed of x is equal to secant times tangent, that's u times v, and then minus v du. And so that gives us our integral. Okay, so we want to look at this integral here because we need to reduce it. We've got secant of u times the tangent squared of u du. Tangent, of course, we've already seen is related to secant by a trig identity. So if I plug in the trig identity for tangent squared, I get secant times secant squared minus 1. That's what you get from that trig identity with the tangent squared. And then I can simply distribute this out so that I get secant cubed minus secant of u du. And look, we started with secant cubed, and we have another secant cubed over here. So if I multiply all this out, I've got secant cubed, that's what we started with, is secant tangent, that's the uv, and then this part is what you got from doing the v du. And we ended up with a secant cubed of u du, and then an extra secant of u. But this term, I've got secant cubed over here, minus secant cubed over there. I can move that over and combine these two terms. So again, this is where we started. I'm going to take this secant squared over here and combine it over there. And so that gives me 2 of this integral of secant cubed of u is equal to secant tangent plus the integral of secant of u du. And you can do the integral of the secant of u du, and what you get for that is that it's the natural log of the secant plus the tangent. And that comes from writing this as 1 over cosine and doing substitution, but I think it's already gotten pretty hairy at this point. But you can see how this comes about, and this is the integral that you get from doing the secant cubed. So we have our integral now done out in terms of our substitution variable u. Doing the change of limits is not so easy in this one, so we're going to convert it back into x. We can note that this value secant times tangent, well, this trig identity here, square root of tangent squared plus 1, that's secant, and then times tangent. We have seen previously from our original substitution that tangent of u is equal to 2x. and that tangent squared of u plus 1 is equal to 4x squared plus 1. And so we can simply plug those values in everywhere. And when we do this integral, we get 1/4 times, by the way, so this was for our original integral. We had 1/2 secant cubed that we had to evaluate, and the secant cubed is 1/2, so I have 1/2 here times 1/2. That's where this 1/4 comes from. And these come from just plugging in those values. And then, of course, our limits of integration are going to be x equals 0 and x equal 1. And when you plug those values in, x equals to 0, this term is 0, so this whole term goes away. And I plug in x equal to 0 here. I'm left with the natural log of 1, which is 0. So when x is equal to 0, this whole term is 0. When x is equal to 1, you simply plug it in, take the natural log, multiply everything together, add it all together, and what you end up with is 1.479. And so that is what you get when you do the integration for the denominator. So if we plug in these values for the numerator and the denominator, we end up with the value for our centroid being 0.5735. So about 0.6, not smack dab in the middle. Why is that? Because this function is increasing rapidly as you increase x. And so there's more line from here to there than there is from there to there. And so I think you can kind of see that visually, and this tells you the point where the average position of that line would be. So that was a pretty tricky example. Let's do another one that's maybe a little bit more simple, although it might require a little bit more cleverness on our part to work. This is the example of a semicircular arc. So I have a half of a circle here, and I want to find the centroid, the x-centroid of this arc. Obviously, we can see that by symmetry, the y-centroid is going to be 0. The z-centroid coming out of the board would be 0 as well, because this is in the xy plane. And so the centroid is going to be only along the x-axis here, and that's what we want to locate. The way that we do this is we're going to break our arc again into little segments of dl. But rather than writing them in terms of x and y, because we're dealing with a circle, it makes more sense to use plane polar coordinates. So if I have a radius going from the origin out to this point here, and I increase the angle by some d theta, the length of this pink segment here is going to be r times d theta, where r is the length of the radius, and d theta gives us the angle change, and we know the relationship between the arc length and the angle and the radius is given just by that. And then we know where this little piece is in an x location r cosine of theta. That comes just by, here's my r, I want to know what the x value is, so I just project it down to the x-axis, and here I have a little triangle. So this side would be the sine, that side would go as the cosine, and the length is just r times the cosine of theta. And so here's the formula that we want to apply, x dl divided by dl. We have our dl converted into r d theta. We have our x expressed in terms of theta as well, and so we can simply integrate over theta. Now, what are our limits of integration going to be? Well, our integration is going to be over d theta, so what does theta range from? If I start here and go up, that would be an angle of pi over 2. But that would only cover half of the semicircle. So I need to actually start here, where x is equal to 0, and I'm going to be starting actually at theta equal to negative pi over 2, and I'm going to go along this arc up to theta equals to positive pi over 2. And so those are going to be the limits of our integration. So here I have simply plugged those values in. We have minus pi over 2 to pi over 2, r cosine of theta, that's my x, r d theta is my dl. Down here I have the same limits, and I've got my dl again as r d theta. I've got an r here and an r there that will combine to be r squared. The integral of cosine of theta is just sine of theta. The integral of d theta is just theta, and so that gives me my integration. I plug in my limits, and I end up with 2r over pi, and that's the answer. That's the centroid of the semicircular arc.